So let's give an example of solving a heat equation problem. Our heat equation is this. It's a partial differential equation which tells us how heat diffuses in a material. I'm imagining a long metal rod. At location x equals 0 and location x equals L, the boundaries of my rod, I have these boundary conditions that the temperature has to be held constant at 0 at the endpoints. This third condition written gives me the initial temperature distribution. At time t equals 0, I have some distribution which gives me the temperature at each location in the rod. So we're going to solve this, and in order to solve, we're going to start with the following educated guess. We're going to assume that our function u that we're looking for can be expressed as a product of functions of t times functions of x. This is really just an educated guess, and if it doesn't work, we'd have to go back to the drawing board and try a new form of the solution, but luckily this will work. If I make this assumption, then I can plug this into our differential equation, our partial differential equation, and find that capital T prime x, that's the left side, because when I take the partial derivative with respect to t, I could treat all the x variables like a constant. That should equal k times the second derivative with respect to x. In this case, I could treat t like a constant, and I get tx double prime. Now, I'm going to separate the variables. The following approach is known as separation of variables because I put all the little t's on one side of the equation. I can write it as t prime divided by kt, and I'll put all the little x's on the other side. So I get x double prime divided by capital X. Now the only way that the left side could equal the right side is if they're both equal to a constant. The left side of the equation is a function of little t. This left side only involves little t's and maybe constants. The right side of the equation only involves little x's. So this right side of the equation cannot involve t's. The left side of the equation cannot involve x's. So the only way that the two expressions could actually equal is if they're both equal to a single constant. And we call that constant negative lambda. This is just a number, and I put a negative in front just because I know what's going to happen in the future, but everything would follow through if you didn't have this negative. Okay, now we have two differential equations. Thus, we have equation 1, a t equation. That's t prime is equal to negative lambda kt, and 2, I have an x equation. X double prime is negative lambda x. And for the second equation, I'm going to include the boundary conditions. So I'm going to include the fact that if I plug in x equals 0, I get out 0. In other words, capital X of 0 is 0, and capital X of L should also equal 0. Okay, so now I'm going to solve each differential equation, no longer a partial differential equation. I'm going to solve each differential equation separately and write my final answer as the product of my two solutions. So the solution to 1 is t is e to the negative lambda k little t times a constant. So you can solve the differential equation in 1 through a variety of methods. It's probably one of the easiest differential equations to solve. You could use Laplace transforms, for example, and you get this as the solution. Now the solution to 2 I'm going to solve on this side here. So I'd like to find the solution. And to do that, I'm going to come over here on a separate piece of paper and solve. So I wrote the equation and the boundary conditions down. And to solve this, I'm going to break the problem into 3 cases. So here is case 1 to solve this differential equation. Maybe lambda is negative. So if lambda is negative, you can solve this differential equation, and then you get capital X is equal to C1 e to the square root of negative lambda x plus C2 e to the negative square root of negative lambda x. Now, lambda is negative, therefore negative lambda is positive, and I actually have e to a real exponent, no complex numbers involved. Now I can use the boundary conditions. So the boundary conditions say I get 0 if I plug in x equals 0. If I plug in x equals 0 here, I get C1 plus C2. If I plug in L, I also get 0. That would give me C1 e to the square root of negative lambda L plus C2 e to the negative square root of lambda L. This gives me two equations and two unknowns. The unknowns are the constants C1 and C2. So you can solve for those constants and find that C1 and C2 both have to equal 0. That means that my solution is just 0. C1 and C2 are 0. That means the whole thing is 0. In other words, I don't get an interesting solution in case 1. So I'm going to ignore case 1 and conclude that lambda cannot be negative. Case 2. Lambda might equal 0. If lambda is 0, then I solve my original differential equation, and the original differential equation just becomes x double prime is 0. That has solution C1x plus C2. Now I use my initial conditions, so 0 is what I get when I plug in 0 for x. That gives me C2 is 0. If I plug in L, I also get 0. So that's C1L, and I already found out C2 is 0, so I don't need to write that down. Therefore, again, I find C1 and C2 are 0. Thus, my solution in this case, again, boring. I don't like the 0 solution. Maybe I'll get something interesting in the last case. That's when lambda is positive. So if lambda is positive, you can solve the resulting differential equation through a number of means, Laplace transforms, for example. Then you get the general form of the solution is C1 cosine square root of lambda x plus C2 sine square root of lambda x. Okay, well now this time I can plug in my boundary conditions, and I get cosine of 0 is 1, so I get C1, and sine of 0 is 0. So I found C1 is equal to 0. The second condition, when I plug in L, this gives me, well, C1 is 0, so I don't need to write that term down anymore. I get C2 sine square root of lambda times L. Now I want this to be non-zero, because I don't want to get another boring answer. That means I don't want C2 to be 0. I want this sine function to be 0. Sine is 0 when the argument is an integer multiple of pi. So we want the square root of lambda times L, which must be a positive number because lambda is positive, L is the length of the rod, that's positive. So I need this to be a positive integer multiple of pi. So this is equal to n pi, where n can be equal to 1, 2, 3, and so on. I don't want 0 because I already concluded in case 2 that doesn't give me an interesting answer. So n could be a non-negative integer. And if I solve for lambda, I get n pi over L squared. In this case, I actually do get a solution. So my solution is x of x is some constant, c2, times sine n pi over L x, and that happens when lambda is n pi over L squared. This is starting to look familiar from our work with Fourier series, I hope. Okay, so I, on the side here, solved this problem. Let me go back to our main problem now. So if you remember where we were, I had these two differential equations. I solved the first one pretty easily, and now I solved the second one as well. Let me write in my solution. My solution is c2 sine n pi over Lx, and that requires the lambda to be n pi over L squared. So that means I have an infinite number of solutions. One for each value of n. N could be 1, 2, 3, and so on. And for every value of n, I have an x and a resulting t. Thus, the general solution to my differential equation is the following. U of tx, I'm going to add together all of the solutions I found, all of the solutions when n is 1, 2, 3, and so on. So I'm going to write a big sum where n goes from 1 to infinity. Then I have the product of t times x. That's what I was assuming my solution looked like, t times x. So these multiplied together give me a solution. So I'm going to put the constant c times c2, I'm going to say that's the constant bn. And I'm going to multiply this e function, e to the negative lambda, which lambda has to be n pi over L squared, times k little t, that's this function here, times the x function, which is sine of n pi over L x. So this is my general solution to this heat equation. Now, what are the constants Bn? Well, the only thing I haven't used yet is the fact that the initial temperature distribution is given by this function f. So, plugging that in, the function f of x is equal to u of 0x. So I'm going to take this expression and plug in t equals 0. If I plug in t equals 0, this exponential function is just 1. So I get the sum, n going from 1 to infinity, of bn sine n pi over L x. So I'm expressing my function as a linear combination of sines. The sine functions are an orthogonal family on the interval from 0 to L. So since sine pi over Lx, sine 2 pi over Lx, and so on, is an orthogonal family, on the interval from 0 to L, I could tell you what those coefficients Bn are. They're just what you get by taking the projection of f onto this orthogonal family. The coefficients Bn are equal to the inner product of f with sine n pi over Lx divided by the inner product of sine n pi over Lx with itself. And I'll explicitly write down what this is. This top part is the integral from 0 to L, that's my interval here, of f of x sine n pi over Lx. And if you do this integral which is sine squared on the interval from 0 to L, you get L divided by 2. When we did the Fourier series, we're on the interval from negative L to L, and so we got 1 over L, but here we have half the length of the interval, so we have 1 over L over 2. This is the final answer. So what is the solution to the heat equation? The solution is this function here, where the constant Bn is given by this integral equation. All right, just to recap, because this was kind of a lengthy process, here's what happened. We had the heat equation. We assumed that we can write the solution this way. We separated the variables, all the little t's on one side of the equation, all the little x's on the other. Once you have that expression, the result has to equal a constant. We called that constant negative lambda. This gave rise to our two differential equations, which we then solved. Solving the second differential equation, I broke into cases where lambda could be negative, 0, or positive, and the boundary conditions only gave me one non-zero solution, which was this. Therefore, the general solution were all linear combinations of these when n could range over any value 1 on. And the last step was to find the coefficients using the initial condition and the orthogonality of the sine functions. All right, excellent. We'll do more examples in the following videos. Follow me along there.